All right, so this is Josh, and I'll be sort of doing a demo of this terrain mapping setup that I created for Aero 465 for my project. So I'll go through how it works and then show you some of the results on Matlab. The SD card is not working because the card does not actually insert into the reader, so I'm using the serial reader.m to just get the results directly in Matlab, which works fine. So I'll talk about first the jig that I set up. So you can see there's two 3D printed components. One of them is a plate and one of them is sort of a servo cradle that holds this servo motor. And the reason the plate's shaped like this is because originally I was intending to have the Arduino and breadboard attached to it, but that was just too heavy and the blades of these servo motors aren't stiff enough to deal with that, so there was some unwanted bending which was throwing off the measurements. So I just took them off, put them on the table, and it works okay, just like that. So the ultrasonic sensor is attached to the bottom, and you can see there's two servo motors. So this servo motor rotates about the local x-axis, this one rotates about the local y-axis. So I'm going to call this servo motor here servo y and this one servo x. So what it's going to do is it's going to rotate. It has 2 degrees of freedom both in x and y. So this is going to rotate the ultrasonic sensor sort of in a spherical pattern. It's going to scan what the ground looks like. So I put a seashell on the floor, or I guess on this desk. Seashell has some curvature to it, so hopefully we'll see some curvature in the map terrain that's generated on Matlab as a surface plot. These two chopsticks are acting as a structural support, and they're held down by this water bottle that is being pulled by gravity. So this servo motor doesn't move as the rotation occurs. Now let's go into some of the math. So how are we actually getting what the floor looks like? So to do that, we have 4 different reference frames. The first reference frame is located on the desk, and it's an inertial frame. It doesn't move. So it's located at the desk, and it's located when this ultrasonic sensor is pointed directly down at 0 degrees. So both these servo motors are at 0 degrees, and the ultrasonic sensor is pointed straight down. That's where the origin of the inertial reference frame is located. Now, we also have 3 other reference frames. One of them is attached to the blade of this servo motor, and it rotates with the blade as it spins. One of them is attached to the body of the servo motor, so it doesn't rotate with the blade as it spins, but it rotates with the entire servo motor as it spins. And this whole servo motor spins because this one will spin it around the x-axis. And we also have a reference frame that's attached to the blade of this servo motor, and that spins with the blade of this servo motor. So how does this work? Well, the ultrasonic sensor is going to take a measurement, and that measurement is going to be a purely z component of a vector in the blade fixed reference frame of this servo motor. So because that reference frame is spinning with the blade, it makes it really convenient because the z-axis is always aligned in the direction of the blade. So whatever measurement this ultrasonic sensor takes is going to be purely a z component in that reference frame. And we know that the angle that this servo motor is going to rotate its blade. So if we just rotate back by an angle of negative theta about the y-axis, then we can get measurement of this ultrasonic sensor in the body fix reference frame of this servo motor, not the blade fix, but the body fix. And that's convenient because this servo motor is going to rotate with the blade of this servo motor. So no matter what the rotation looks like, the reference frame attached to the blade of this servo motor and the reference frame attached to the body of this servo motor are always going to be aligned. So the vector from the center of this blade to the center of the body of this servo motor is always going to be constant with respect to servo X's reference frame. So what are we doing? We're taking the measurement of this ultrasonic sensor. We're getting a vector that's purely a z component in the blade fixed reference frame of servo Y. We're rotating that z component in servo Y's blade fixed reference frame to the body fixed reference frame of servo Y, which is aligned with servo X's blade's reference frame. So we're rotating the ultrasonic sensor measurement into servo X's reference frame. And now all we have to do is we know the angle that servo X turns. So if we rotate servo X by an angle of negative phi about the x-axis, well, that's just going to get us back to the inertial frame. So effectively we can get, using some vector subtraction, we can get what the ground looks like according to the ultrasonic sensor as a vector in the inertial frame, and we can plot that point, and we can generate a surface plot in Matlab. So that's the basics of how it works. In order to generate the surface plot, the data is passed through a Kalman filter, and it's also some additional processing is done to remove any outliers of the sensor. The sensor is pretty bad. The covariance is pretty high. It'll be reading, 3 centimeters consistently, and all of a sudden it'll read 1,000 centimeters. So some processing is done to remove extreme outliers like that, and then it's all passed through a Kalman filter to get sort of a smoother version of the of the surface plot. So I'm going to press run, and I'm going to let this run, and you'll see how it works. It will sweep from 0 to 45 degrees in both directions. For every 2 degrees that this servo blade turns, this one's going to sweep the entire 90 degrees in theta. And it'll do that until this has gone, this servo motor has rotated to 90 degrees as well. So I'm going to run it, and as I run it, you'll see how it behaves, and I'll sort of be commenting throughout. So let's press run. You can see briefly there, it turned to the nominal position, and it collected data to acquire what PKM is, so our initial measurement error. And now we're sweeping the ground, it's scanning what does the floor look like. So sometimes you have to come and make sure the servo blader is popped in so it doesn't fall off. But it's going pretty quickly. You'll see it'll start to lag at some points because the tensions in the wire are slowing the sensor down and slowing the motor down, but it still works in general. And you can also pull up on this bar to get rid of any unwanted bending, but not very important. You can see this servo motor is very slowly moving 2 degrees at a time every time that a full sweep is completed in theta. So we're going from negative 45 degrees, now we're approaching 0 degrees, and then we're going to end up at positive 45 degrees in phi. Make sure this is popped in again. All this dental floss is holding the jig together, making sure the servo doesn't fall off the cradle, making sure the plate doesn't fall off the servo. And we're slowly getting there. You can see that there's quite a bit of vibration as the servo motors move. That is probably a primary source of some of the error that we see. It's kind of hard to fix that, especially when you just have, sort of these cheap servo blades. I think if the servo blades were made of metal, this would actually be a way better experiment. We would see more stiffness and not as much bending, not as much vibration. We're starting to approach the end of the cycle. It's probably got 3 or 4 more rotations in phi, and then I'll show the surface plot in Matlab. Yeah, so it has finished. Now Matlab's going to draw out the surface plot, and it takes a little bit of time. There you go. All right. So I have 2 plots here. One of them is from the last time I ran this, and one of them is from this time. So I'll get to kind of examine both of them separately. So here we go. This is the one that just got generated. So you can see on the left side, it's detecting that wall. So there's a spike in elevation because the sensor is actually picking up this jig, and it's saying that the elevation is pretty high right there. And that's going up to 6 centimeters, which is actually a really accurate estimate. I've measured how high this jig is. It's about 6 centimeters tall. So it's mapping that properly. And you can see on the right hand side, it's starting to pick up on this shell. So if we look at what is the height right here on this shell, well, one of these points is about at 4.5 centimeters. If I were to go actually here and measure this, it's hard to do it with this pen but I would say that's about, let's see, that's 1/200th. That's about 3 centimeters, so it's a centimeter off. The previous plot that I had done when I ran this before this demo is actually a better representation because you get a really clearly defined wall on the left side, and then you get that trough in the middle. So, you know, it's picking up this jig and it's picking up this sort of empty space right here between the jig and the shell. And then on the right hand side, you can see it is starting to pick up on sort of the curvature of that shell right there. So right here we have some elevation changes in the shell, and you can actually see a small, you know, it goes up right here and then down and then back up, and that's sort of the behavior of the shell, what it actually looks like. And this plot is showing that to be about 4 centimeters, which is much closer to the actual measurement of the height of the shell. So that's sort of how this this instrument works. And you know, ways to improve it would be to use stiffer servo blades, have probably a less janky jig, one that is more structured and rigid, and a better ultrasonic sensor that doesn't have as much noise and has a higher resolution for each degree of rotation. So that's my project, and thank you for listening. I also read a report on it. I'm going deeper into the math, so on Canvas, if you need more information, that's where you'll find it. So thank you.